First thing you should do is find this set of guided notes. And you can see it's kind of set up like a chart where we're going to compare solar and lunar eclipses. First a description, then a sketch, and so on, right? So we'll start with some basic information about eclipses in general. Then we'll focus on solar eclipses and then on lunar eclipses. So in my opinion, an eclipse of the sun, a total eclipse of the sun, like this photo shows, is one of the most incredible things you can ever witness in nature. They're actually not that rare worldwide. Like there's an eclipse like this every year and a half or so. But to be there is difficult. You have to be in the right place at the right time, so it makes it a pretty unique event. So we're going to talk about both solar and lunar eclipses. We're going to talk about how they're caused and what happens from our viewpoint. So the alignment has to be just right for the Earth to pass through the moon's shadow or for the moon to pass through Earth's shadow. That's what an eclipse is we're moving through the shadow of the other object. So there are two types of eclipses, solar and lunar. And the name means a solar eclipse means the sun goes dark. A lunar eclipse means the moon goes dark. So here are some diagrams and descriptions. What is this doing? Okay, looks like I've got this. There we go, that's better. So here's the description at the bottom of them. That's the description I'm looking for on your notes at the bottom of each of those diagrams. I'm going to do that. So for a solar eclipse, the moon's shadow hits the Earth, blocking out our view of the sun. The moon's shadow hits the Earth, blocking out our view of the sun. On the other hand, in a lunar eclipse, the Earth's shadow covers the moon, and so the moon gets dark. And this slide is also what I'd like you to use for your diagrams. And I think what I will do is switch to the PDF so you can see how I would make these diagrams using the PDF. So in a solar eclipse, did you guys finish the description or should I go back? Yeah, I'm sorry, I went too fast, huh? So I've been lucky enough to see a few solar eclipses and quite a few lunar eclipses. Lunar eclipses are a little easier to see than solar eclipses. For a solar eclipse, usually you have to travel somewhere to see it. So if you look at this diagram, you can see that the moon's shadow makes just this tiny little point on the Earth. You have to be in that point to see the total solar eclipse. Meanwhile, the partial eclipse is visible over a wide region of the Earth. Sometimes people are like, well, why should I travel to see the total eclipse when it's going to be a partial here? It's going to be just as good, and that is not true. A partial eclipse is nice. A total eclipse is magic. It's incredible. But you got to go out of your way to see it. So let's look at how these occur. So what I'm going to do is I'm going to start by making the sun. And then I'm going to make a very small circle to represent the moon. And a medium-sized circle to represent the Earth. Next, I need to draw some arrows to show the sunlight. So what happens is because the sun and the moon really are quite large, right? We need to draw the sunlight coming from both sides of the sun and converging together on this one point on Earth. So I'm going to do my arrows like this, and then I'm going to move my circles to match a little better, supposedly. That's better. And I'm also going to make my moon a little bigger to show it blocking off more of the sunlight. Then I'm going to make one more circle, and I'm going to fill it in so it's solid. This will be the moon's shadow. And it doesn't matter what color you use. I'm just trying to save time by using whatever color is there. So you have to be within that circle, the darkened circle, to see the eclipse. If you're not inside that circle, you would not see the eclipse. That's the complete shadow of the moon. And I've drawn that shadow much bigger than it actually is. It would be a circle because the moon is circular, but it's only maybe 50 miles across, and you have to be inside that small zone. Now, of course, the Earth is also rotating while this is happening. So the best way to think about where you would need to be during an eclipse, I think, is if we look at this globe, and I'm spinning the globe, and I took a marker and I touched the globe while it was spinning, wouldn't it draw a line on the globe? But the marker is only that one little circle, isn't it? Right? Or I could use this eraser. Right there, it's eclipsing, But as the Earth turns, all those areas were eclipsed, weren't they? Because the Earth is turning underneath the moon's shadow for a little while. So it ends up being a stripe, not just a circle. But you have to be in that stripe to see it. So I would like you to do a sketch in a similar way that we did this one to represent the lunar eclipse. The difference is now Earth is in the middle. Instead of the moon being in the middle, like we just drew, although I put the sun on the other side, didn't I? Instead of the moon being in the middle, now the Earth is in the middle. And the entire moon ends up inside the shadow. You don't have to draw a dark circle on the moon because the whole moon gets eclipsed at once by our shadow. So one way or another, either the Earth is moving through the moon's shadow or the moon is moving through Earth's shadow. And from our viewpoint, this darkens either the sun or the moon. So look carefully at this diagram, the way it shows the sunlight forming this shadow of the moon that only hits a small part of Earth at one time. But on the lunar eclipse, the entire Earth's shadow blocks out all of the moon at the same time. That's because the Earth is so much bigger than the moon. So the moon can fit entirely within Earth's shadow. You might think that this would happen every month as the moon is circling the Earth. And it would, except that the moon's orbit is not in line with the Earth's orbit. The Earth's orbit is like a disk at one angle, and the moon's orbit is a disk at another angle. So only where the two disks cross could you have an eclipse. Normally the moon is either too high or too low compared to our orbit, either above our orbit or below our orbit, and we wouldn't see an eclipse. But when it crosses our orbit, if it's full moon or new moon, then you can have an eclipse. Okay, and then there's the next thing is about their visibility. In other words, how easy are they to see? So you're going to compare the time and place. So look at this diagram. Sunlight from the top of the sun is released and it follows a wide band of pathways hitting both the top and the bottom of the moon, right? And that throws this shadow on the Earth. Meanwhile, from the other side, it throws that shadow. Where they both overlap is where you get the total solar eclipse. Have you ever noticed, like, when there's two lights on, there's like two shadows, and where they cross is where it's a completely dark shadow? That's what we're talking about here, like a partial versus a complete shadow. In fact, I don't know, is it happening back here? See a shadow of my hand at all? Not very well. I kind of see one from these chairs, though. Can you see where there's more than one shadow of the legs of the chair? And right here, it's extra dark in the middle, but it's kind of faded on the sides, isn't it? This is where you have to be for a total eclipse, is in that double overlapping shadow. So if you're in the double overlapping shadow, that's where you are to see a total eclipse. It's just a very small point on Earth, isn't it? So you have to be inside that circle about 50 miles across to see a total eclipse. So when it talks about visibility, time, and place, you have to be within a small circle, 50 miles across, to see the total eclipse of the sun. That's what I mean by place. So I guess for that, you could say limited locations on Earth would be an easy way to say it for that section. We'll come back to time in a minute. Oh, here it is right here. And it only lasts between 2 and 7 minutes in any one place. So visibility in time and place, it's quite limited for a solar eclipse. Only a couple of minutes of complete darkness with the sun being blocked out. Also, you have to be at a very limited location. So for a solar eclipse, it's short and in only a certain place. However, it always starts and ends with a partial eclipse. Somehow you have to get to this where these yellow lines intersect, so you must be going through the purple part too on the way. So you would see a partial eclipse at the beginning, then you'd see a total eclipse for just a few minutes, and then you'd see another partial eclipse at the end as the moon's shadow crosses over you. So that's another way to think of it. You're standing there on Earth. Imagine like the shadow of a cloud moves over you, right? But this is the shadow of the moon moving over you. So the moon's circular shadow moves over the planet quickly because of our rotation. Kind of like holding a pencil on a spinning globe. It only hits one point for any one moment. Now, there are some astronomers who have chartered a jet to fly inside of the shadow, and they've been able to study the total eclipse for like an hour and a half. But if you're just on the ground, the most you would ever see is like 7 minutes long of totality. Anybody see the eclipse in 2017, a couple summers ago? Where did you see it? Where? At your middle school? And where was that? What state? Oh, so you saw it here in Nevada. So you saw a partial eclipse. Yeah. I went to Oregon to see the total eclipse because it wasn't total here. I've traveled a little bit specifically to see eclipses. So here's a nice view showing what we're talking about. This is the shadow of the moon moving over the Earth. Actually, the Earth would be rotating too. So back here is the night side of the Earth, right? Over here on the back. That's the nighttime side of the Earth. This big bluish gray region is where you could see the partial eclipse. But to see the total eclipse, you would have to be within the red circle on here. Only on the red dot, somewhere on that red dot, would you actually see a total eclipse. And this was 2012. Notice it actually hits us. There was a total eclipse that hit Tahoe in 2012, although it was a different kind of total eclipse that is less spectacular, but in a way more unusual. And I'll talk about that in a minute. So my first eclipse was in Eastern Washington. I was going to college, Washington State University, and there was an eclipse coming, and we were all excited, and we got up in the morning, and it was cloudy. So did I get to see the eclipse? Not through the clouds. So what happened for us was sun came up and the birds were singing and stuff, and then it got dark because that much of the eclipse you could see, right? you couldn't see the sun and so forth in its parts, but it got dark, and that made the birds stop singing for a few minutes while it was dark, because it's as dark as nighttime. So it got light, I don't know, 6 in the morning. Total eclipse was around 9, so it got dark and the birds stopped singing. And then 10 minutes later, it got light again and they started singing again. That was my first one. But my best one was this one. This was an incredible experience. So there was this big eclipse coming. And when I mean big, it means it was going to be dark for a long time. This one was 6 minutes and 53 seconds if you were right in the center of it, which I wasn't, but still I had like 6 minutes and 40 seconds of complete darkness. So in planning for this, I decided to go to the very tip of Baja California down here. A lot of people went to Hawaii, but it was more likely to be cloudy in Hawaii. So I decided to go to Mexico instead. And I drove. I kind of was in a small caravan of a couple of people, and I rented a little Volkswagen at the Tijuana airport, and then we drove the 1,000 miles down to the tip of the Baja Peninsula, camping along the way. Incredible desert scenery too. And then when we got to the campground down here at the bottom where we were going to see the total eclipse, there were tons of people there. And this whole campground was filled with people that came there specifically to see the eclipse. And most of them had telescopes. I had that little red telescope that you saw in the video. I didn't have my big telescope yet, though, which would have taken a lot of room, would have been difficult to transport. At any rate, the little telescope was good because I could attach my camera to it, and I took some photos, which was cool. But anyway, we were in the campground for a week before the eclipse, and at nighttime you could walk around and people had their telescopes up and they'd invite you over to look. It's like, oh, I'm looking at Venus. You want to see? Oh, I'm looking at the rings of Saturn. Oh, I'm looking at the Orion Nebula. It was awesome. People would invite you in to look at whatever their telescope was set up to do. Then was the day of the eclipse, and this was July 1991. July in Baja is hot, and the eclipse was at about noon. And the temperature, well, first thing in the morning, it was cloudy, and so we were pretty worried we might not see it. But then the clouds cleared, the temperature rose up to like 105, and then when we got hit by the shadow of the moon, it was dark enough to see Venus and other planets and bright stars at noon. And the temperature dropped to like 90. It dropped 15 degrees in the 6 minutes of darkness that we had. It was amazing. And then took a week to drive home. A lot of people, it seemed like the rich people would just fly there for the 5 minutes of eclipse and then leave. But I'm really glad I went there and explored a lot more. You know, it's kind of risky. If you're going to travel to see an eclipse and it's cloudy, you're screwed, huh? But if you plan other things around your trip, then it can be worthwhile. So notice it's a two-part shadow. There was a full-on partial eclipse over all of North America at the same time, but only the total eclipse on this dark line, right? And these two parts of the shadow have different names. In fact, I think you should go to the bottom of your notes, very bottom of page 1, and it's going to ask you about the umbra and the penumbra. So go ahead and use these to describe those two parts of the shadow, umbra versus penumbra. So as I was pointing out with the shadow of the chair back there, the completely dark part is the umbra. That's where you have to be to see the total eclipse. And you should be filling in umbra versus penumbra right now. Now, surrounding the umbra, the complete shadow, is the penumbra, and that's where you can see a partial eclipse. Now, the farther towards the total eclipse than you are, even if you're not in it, the higher percentage of eclipse you would see. So like if you were halfway between the edge of the penumbra and the umbra, you'd get a 50% blocking of the sun. If you were closer than that, you might get a 75% darkening. But like I said, the difference between even 95% and 100% is the difference between that's cool and astounding, incredible experience. So I have found it way worthwhile to travel to see total eclipses. Um, a few years later, I went to see another one in Peru. And of course, while I was there, I visited Machu Picchu and the Inca ruins and stuff. And then I went to Oregon a couple of years ago to see that one. Let's see, what else have we got here? Oh, here's the eclipse of 2017. So the eclipse began out in the Pacific, ended in the Atlantic, crossed over all of North America. To see the total eclipse, you had to be on this thin red line. That was the only place you could see the total eclipse. Anywhere else, it was going to be partial. Even 95% is not 95% of a total eclipse. I'm going to show you some features that you see in a total eclipse that even 99% partial eclipse you would not see. So if you have the chance, get onto what they call the center line so you can see the total eclipse. Anywhere in the shaded region, you get a nice partial eclipse. And the other thing here is, if you're at the edges, even if you're in the center line, you're going to have a shorter eclipse. Ideally, you want to be as close to the center of that line as possible, both east-west and north-south. Here's a zoomed-in view. So you had to be somewhere on this line, this gray line, to see the total eclipse. If you were on the black line, you would get the maximum amount of totality in your region. But to get the most of all, you had to be right there. That was going to be the longest eclipse, which for this one, I think was like 2 minutes and 40 seconds. Not as long as the one I saw in Baja. But this is about where I was up there in Oregon. But remember, the moon's shadow is moving, kind of like this. Because Earth's rotation is spinning, the moon's shadow ends up looking something like that, moving along the Earth. Does that make sense? So this is really what's happening. There's a circular shadow that crosses different places at different moments, huh? And you've got to be there at the right time. It's too late now, right? If I was in Oregon, I would have missed it there. Right? Got to be at the right time at the right place. Okay. Upcoming solar eclipses in the US. We have 2 of them in the next few years. This looks like a good one to look for to me in 2024. This one looks like an okay one. And the reason I say that is because, do you see the way this diagram shows that sun flaring out there? This is what we think of as a total eclipse. And that's what's incredible to witness. This one is actually more rare, the annular eclipse. And this is the one that went over Reno and Tahoe in 2012. Annular, in this case, does not mean every year. There's a word, annulus, that means like a donut shape. So the sun would be this yellow circle in the sky. And the reason that happens is the moon is a little further away from Earth, so it looks smaller and it doesn't block out the entire sun. That's what we call an annular eclipse. And they're more rare, but less spectacular than the total eclipse. So what's the difference between a total and a partial eclipse? Is that the next section of your notes, is to compare these two? Okay. So that was a total eclipse that they just showed, huh? This is what you see in a total eclipse. So a total eclipse happens when the sun or the moon is completely blocked due to this perfect alignment of the three bodies, the sun, the moon, and the earth. Completely blocked out. Might not be blocked for long, but it's completely blocked when it is. On the other hand, a partial eclipse is when the sun or moon is only partly covered. They're not quite lined up exactly, but you would see this strange looking crescent shape on the sun or the moon. Every total eclipse begins and ends with a partial eclipse. And every total eclipse, if you're not in the total eclipse path, you can still see a partial eclipse. Now, there's this question about eye protection, right? So, the partial eclipse is dangerous. You need eye protection during a partial eclipse because you're staring at the sun, which can damage your retina. However, during the total eclipse, during those 5 minutes or 2 minutes or whatever it is, you can take off your eye protection and look right at it. Some people think there's some kind of change to the light that comes out in a total eclipse. Basically, what happens is the dangerous light is blocked off. So there's really no difference between staring at the sun on a normal day and staring at it during an eclipse. If you look at the sun long enough, you're going to damage your vision, especially if you're magnifying it at all with a telescope or binoculars. That can definitely burn your retina. So the partial eclipse is more dangerous than the total eclipse. Remember, every total eclipse starts and ends with a partial eclipse. So you need eye protection for the first hour or hour and a half. Then you have 5 minutes when you can look straight at it. And then you need to protect your eyes again for another hour or hour and a half. Of course, if you don't look at the sun, you don't need eye protection. It's not like you need it when you're driving or walking. But anytime you look up at it, you would need that protection. So here's a photo of a partial eclipse. So the sun ends up looking like this crescent. And this is probably something like what you would have seen here in 2017. Basically, this is the moon. We're looking at the moon. We're looking at the shadowed side, the nighttime side of the moon. So we can't see it. That means this only happens during new moon. Remember when we took the ping pong balls and turned them around us with the light coming from over there, for instance, and looked at the different phases? The only time you can have a total eclipse is when the moon is between you and the sun, and that only happens at new moon. So let's see. If this was a total eclipse, the moon would then move in front of the sun and block it off completely, huh? And then it would keep moving and expose the sun again. I think there's a little animation to show this, just with, no, maybe not. Maybe. So the moon slowly crosses in front of the sun. If it lines up perfectly, we get a total eclipse. And there's the moon's path. If it became total, it would have gone in that angle. Does that make sense? If the moon was moving like that, it would block it right there. Right now, it would be total, but then it would go to partial again, huh? Here's another image, and we were debating last class in my fourth period Earth Science whether this is a real photo or not. Maybe it's been enhanced, I'm not sure. Maybe it's at sunset. So a partial eclipse of the sun at sunset. This is what would happen if it was a partial eclipse. So this part of the moon would be moving across the front of the sun, and this bottom part of the sun would never get covered, would it? So that would be partial eclipse. Here's another. Okay. Let's see. Should we jump ahead? I think if you go down a little bit, there's on page 2 there, it asks you about the photosphere. And this is describing the photosphere. The photosphere is the layer of the sun that we can see every day. It's the brightest layer, releasing the light, and that's how it got its name, the photosphere, or the sphere of light. And this is what can damage your vision if you look at it. But it's not like it's any more dangerous than staring at the sun on a normal day. But people are more likely to stare at it for a longer period of time and end up damaging their vision as a result. So if it's a partial eclipse, you need to protect your vision. So we often think of the photosphere as the surface of the sun, because that's what we see. Of course, it doesn't really have a surface, right? It's a big ball of flaming gas. Now here's a nice multiple exposure photo where they overlapped a bunch of photographs of a partial eclipse. Can you see how as the sun was going down, the moon's shadow, it moved further and further into the moon's shadow, didn't it? And this was the point of maximum eclipse here. It looks like it's about maybe 75% blocked off. And then the moon moved out of the alignment with the sun, and by sundown it was a totally, excuse me, it was completely clear again. So that's what you would see during a partial eclipse. You can tell this is probably 3 or 4 hours for that whole series of events to happen. Here's another. This is an awesome photo of a partial eclipse. So what's this dark region down here on the bottom left? What is this? That is the moon, huh? Is this pretty good evidence that the moon is round? Well, of course, we can look at the moon and see that it's round, huh? These things here, these are called sunspots, and we're going to learn more about the sun later. But these are cool regions of the sun where there's a disturbance in its magnetic field. It cools off, and it looks dark against the background of the rest of the sun. They're actually still quite hot and would be glowing if we could look at them by themselves. But compared to the rest of the sun, they're pretty cool. But the coolest thing about this photo is not just the sunspots, but this thing. That's not just some random thing. These people checked ahead with the NASA app to find out when the space station was going to fly by. And they set up their telescope and camera to capture the moment that the space station flew overhead. And basically, isn't the space station also eclipsing the sun right there? Its shadow would be hitting these people, even though we couldn't tell because it's too small. Okay, a total eclipse. Did that finish up everything on that first page? Yeah? Okay, so this is all about page 2, I think. Or maybe there was some stuff to compare partial versus solar. Did you finish the comparison between, excuse me, partial versus total? You finished that? Okay. So, solar eclipses can only occur during a new moon. I think that's at the top of page 2. What moon phase does it need to be? Has to be new moon. This is when the moon is between the sun and the earth, and at the same time that it's new moon, the moon's orbit has to cross Earth's orbit. So it's not every new moon, it's only when they line up. Maybe every 15 or 20 months would this happen. And when I say every 15 or 20 months, I mean somewhere on Earth, not everywhere. So here we're looking at, you could call it the dark side of the moon, but actually it's the far side of the moon. It's the same side that we always see. The Sea of Tranquility is right there where Apollo 11 landed. And there was, what were some of the other things we put on the map? The Sea of Storms, Tycho, the crater Tycho. All these things that we normally see on the moon, they're right there. It's just that they're on the nighttime side of the moon, so they're not lit up and we can't see them, huh? Now this is pretty incredible. I think there's something about numbers on the notes, right? What did it say? Size and distance ratios. So, incredibly, the moon is 400 times smaller than the sun in our viewpoint. Well, actually, in reality, the moon is 400 times smaller than the sun, but it's also 400 times closer to us. And that means they look like they're about the same size in the sky. The moon is 400 times smaller, but it's also 400 times closer, which makes it look bigger. Since they're both 400 times, it makes the moon and sun look about the same size, and we get this amazing, spectacular solar eclipse. If the moon was closer or bigger, it would block off more of this, wouldn't it? If the moon was smaller or further away, it wouldn't block off the entire photosphere, and we'd only have that annular eclipse, which is less exciting, if you ask me. So, pretty amazing coincidence that it's 400 times smaller and 400 times further away. What else do we have here? Okay, here's something about the corona. This thin outer atmosphere, which is only visible during a total eclipse. Normally, the photosphere is too bright, and so you can't see the corona. It is always there. But usually we can't see it because it's too bright. It's like if somebody held up a candle in front of a car's headlights. You wouldn't be able to see the candle because the car's headlights are so bright that it would just disappear. The corona is not just a smooth sphere around the sun. It has these extensions that are called coronal streamers. And the coronal streamers are where the solar wind begins. So there's your coronal streamers. Write something down about those. Projections of the corona that start the solar wind would be something good to say. Oh, and of course, let's talk about this word corona because we've been hearing it in terms of a virus so much, huh? In Latin, corona means crown. And so the corona is considered the crown of the sun. And you might have seen some other coronas around, right? Notice the corona beer has what symbol? Right? And the coronavirus is a crown of little protein projecting from its surface. This is what the vaccine does. The vaccine mimics these proteins that stick off of the surface of the virus. And as a result, your body recognizes those and attacks them whenever it sees them. So that's how it protects you from the coronavirus, is your body is primed by the vaccine to attack any of those corona proteins that it sees. All right, now here's another type of photograph. Notice all the red and pink in this one, huh? And this one that we just looked at has all this corona streaming off of it, huh? But not very much red and pink. But this one's the opposite. It's got all this red and pink, but not very much corona. What's going on is that a camera is really only sensitive to a certain amount of light. And you can set your camera up to take a picture of the corona or of these red prominences, but not really both at the same time. Your eye can see both at the same time, though. Your eye's better than a camera. So these eruptions of hot pink gases are called prominences. Is that one of the things on there? Yeah, prominences are on there along with the chromosphere. So these erupting hot pink gases, this is their true color, are called prominences. And look at this one here. Do you see that white spot in the middle of it? That's about the size of the Earth. So these are massive eruptions coming off of the surface of the sun. Bigger than the Earth. There's the Earth size for comparison. Let's see. I think I already said this. Now this is safe to look at with naked eye, right? Because the photosphere is blocked. But above the photosphere, reaching further away, is this layer called the chromosphere, or the sphere of color. It's called the sphere of color because it has this hot pink appearance. Remember we did the atomic spectra. The spectrum of these gases, they're mostly hydrogen, and so it's giving off this pink light. And once again, you can only see this during the total solar eclipse because the photosphere is normally too bright for it. So you want to describe the prominences and the chromosphere. So the chromosphere is above the photosphere, but below the corona. Sphere of color. Right. So I think these are some images of total solar eclipses. Oh, not quite. Look at that. This is called the diamond ring effect. Do you see why? And this is the very last moment of a partial eclipse before the total eclipse. So this is pretty cool to see. And it only lasts a flash and it's over. Because as the moon is moving in front of the sun, you get this last little view of the sun right here. And you're starting to see the corona around the back side. So this is the very beginning, also the very ending of a total solar eclipse, is this diamond ring effect. You can see one little last piece of the photosphere And we think what's going on is it's shining between some mountains. Up on the moon, there are some mountains, and a little bit of light is going between the two peaks. And you should not look at this directly because that is the photosphere. All right, so here's a progression of a total solar eclipse. It starts off down here, and do you notice that it's the right side of the sun that's missing? You see that? And then at totality, the whole thing is missing. And then at the end, it's the left side that's missing, isn't it? It's because the moon is moving in front of the sun, blocking off one side, then the whole thing, and then the other side. So I think on your notes, you're supposed to label the stages of those photos. And you need to label, of course, the total solar eclipse. Where would that be? It's the total eclipse. Label that number. And then you're going to label partial eclipse twice, but you should label partial eclipse at start and partial eclipse at the end. And then you're going to have, what is the very last moment before the eclipse begins? Very last moment before the total eclipse begins is diamond ring effect. You're going to have that on there twice also. So it should say diamond ring effect at start of totality and diamond ring effect at end of totality. So the whole thing lasts about 4 hours. The total stage is only about 5 minutes. The diamond ring is probably 10 seconds. So ancient cultures had a variety of beliefs about eclipses. We already talked about how Stonehenge might have been built to predict eclipses. Um, if that's true, imagine how much power you'd have if you were the priest that was going to say, oh, the sun is going to go dark tomorrow, right? Wouldn't that give you a bunch of power over people? On the other hand, the ancient Chinese thought a dragon was eating the sun. In a way, does it look like that during these stages? Like a dragon is eating more and more and more of it, huh? Taking bigger and bigger bites off the sun. And so the emperor would order, well, the royal astronomer would inform the emperor that an eclipse was coming in a month or two or whatever. And then the emperor would order that the entire kingdom gather drums and gongs and make a bunch of noise to chase the dragon away. Fortunately, they were always successful. Another interesting historical event happened several hundred years ago. Europeans were fighting a battle against African tribes. And the Europeans realized an eclipse was going to occur that day. And they figured that it would scare the natives, so called. But this particular tribe liked to fight at night. So they took it as a sign of the gods' favor and wiped out the Europeans. So eclipses have had a big impact on people and our cultures. And yet there's this remarkable coincidence that it might not have even happened if the moon and the sun weren't that 400 times further apart and 400 times smaller. Oh, here's a nice image of what's going on. A little video. So we're just about back to the start. Can you see some sunspots? And it's getting more and more. Meanwhile, it's getting darker and darker. And then we get a diamond ring, a total eclipse, another diamond ring, and then it gets lighter and lighter. And when it's getting darker, it's not like a normal nightfall. There's something weird about it. There's like this strange quality to the light around you. Your surroundings look different. Things are kind of glowing in a way. And I think it's because you're still getting this sunlight, but you're also getting some of the moon's shadow on you. You're standing on the edge of the shadow, and so it's like the light is coming from the side a little bit or something. It's a very strange phenomenon. And then, of course, the totality is magic. Now, here's a view of a total solar eclipse from space. See the dark shadow moving across Africa there? Right? Also, you can see as the Earth is rotating into the nighttime side, huh? That's what we're seeing over here. As the Earth gets darker, that's as we're rotating around. So this view was always from the same direction. Okay, an annular eclipse. Here's a photo of one down at the bottom. And basically the word annulus, as you can see, means a donut or a ring. So an annular eclipse is named after this Latin word for a ring, the annulus. On the other hand, you might think an annular eclipse happens every year because we use that same word to mean yearly, but that is not what it means. It means it's a ring-shaped eclipse, a donut eclipse. So you never see the corona, you never see prominences or coronal streamers. You have to wear eye protection the entire time. And this happens because the moon is just a little further away than normal. So it doesn't block off the entire sun. So we have a ring, an annulus of very bright light. You wouldn't see stars. It wouldn't be dark enough to see the stars. You do get that strange lighting that I was talking about a minute ago. And the sun looks like a big donut, but you never see the corona. We could see one here in 2012, and I think there's one in 2023 coming to North America too. Actually, less common than the total eclipse. Here's the path of the 2012 annular eclipse. And it did cross right over us here. Anywhere within the blue lines, you could see the total. You'd see the most of it if you were on the red line. So we had an annular eclipse here. And I wouldn't travel to see an annular eclipse. I certainly watched it because I was here, but I probably wouldn't have traveled to see that. On the other hand, I would travel to see a total solar eclipse. So here's a photo of what it's like. See the difference between that and a total eclipse? There is no corona streaming out of there. It's just that donut of bright light. No diamond ring effect. Still too bright to look at that safely. Okay. So, from an eclipse chaser, people that travel around the world to see eclipses are eclipse chasers. And the normal rule of thumb in eclipse chasing is that a total solar eclipse is worth any and all effort to see, no matter where it is in the world. An annular eclipse is worth driving or taking a short flight to see. A partial eclipse is worth looking at. Annular eclipses, so named because of the ring shape of the sun, are fun to watch. However, they lack the complete transformation seen during a total solar eclipse. If you live in the western part of the USA, it's worth taking a look to see if you can get to the center line for the annular eclipse coming up in 2023. And now there's this group that puts on a big music festival for every total solar eclipse called Symbiosis. And there was going to be a Symbiosis festival in Argentina last December because there was a total solar eclipse down there. But of course, with Corona, they had to cancel it. I had some friends that went to the Oregon Symbiosis, and they said it was pretty fun. It's like 4 days of this festival, and they plan it to be on the center line to be able to see the total eclipse. And so there's all these people, there's all this music, and then the eclipse happens, kind of the climax of the whole thing. But you got to be smart, not make dumb choices like I did on the swing the other day. So, where to watch? Eclipses of the moon can be seen anywhere on the nighttime side of the Earth, because the whole moon is moving through Earth's shadow in space. A solar eclipse can only be seen from a small spot on the Earth, because the moon's shadow is just that small circle. And then the last thing on that page, eclipse safety. What? How to watch it safely? So, even though the moon is going to hide most of the solar disk, any visible photosphere is still bright enough to cause eye damage during the partial phase. So to view a partial eclipse, you either need to look through really dark welder's glass, you need to build a projector, or you need to have a solar eclipse filter. And what I mean by a projector is simple. It could be as simple as a shoebox with a pinhole in it. And then you could safely see what was going on. Or you get eclipse glasses from Amazon. Now, if you're going to look at it through a telescope or with binoculars, you absolutely must have a specialized filter. Like before the Oregon eclipse, I bought a filter for my big telescope. Just the filter was like $100. But that makes it safe to look at the sun through my big telescope. When I looked at previous eclipses with that telescope, I was using the projection method that I'll show you in a second. You basically shine the light, instead of looking through it, you shine the light into a box. And then you can see that the sun is either a circle when it's normal, or it's a crescent when you're losing part of it from the eclipse. But with that particular telescope that I have, the big circular part of it is cardboard, and the mirror concentrates the light enough that that cardboard starts to smoke if it's not lined up perfectly with the lens. So if the cardboard is burning, imagine what that would do to your eyes if you looked at it directly. Again, the total stage of an eclipse is safe to watch, but you got to be very careful at the end to make sure you put your eye protection back on. So here's the simplest way to go. You just buy one of these solar viewers. There's a fancy filter for a telescope. You cover up the end of it. Or you do this. You make a box and you put a pinhole over here. I think what they did here to make it a nice circular hole was they used a piece of foil, taped some foil to that, put a pinhole in it, and what it does, it throws the sun's shape onto the far side of the box. You cut another hole to be able to look at it. And here you can see that the sun is shaped like a crescent during the eclipse. If it was not during a partial eclipse, you would just see a full circle. So this is the easiest way to go, is just by making the box. Okay, yeah, this is good. So next solar eclipse is just coming up in a few months, but you have to be here. See this blue line right here down in Antarctica? That's the eclipse of 2021. You have to be there to see a total solar eclipse. Here's one for 2024. Each of these lines is a different eclipse. What's this one? This is 2023. That's going to be that annular eclipse, I believe. Yeah. So red is an annular eclipse. Blue is a total eclipse. I'm going to try to see that one in 2024. Probably go to Texas or something. I might choose Texas instead of Maine because it's more likely to rain in Maine, right? Also, Texas is closer to the center of that whole line. Mexico would be good too. Here's the eclipses in North America during the first 50 years of this century. This is the one that I went to Oregon to see. No, this narrow one is. Okay, before we do lunar eclipses, um, let's have a look at these solar eclipse viewers. Oops, sorry. So have you seen these before? So you see that these are basically glasses that you put this thin metal foil on there called mylar. And this really limits the amount of light that comes through. Just look around the room. Can you see anything through them? Even looking at the lights, look up at the lights. Can you see the light coming through those? I can't see the light through there. I can see the light around there, but I can't see it through there. Okay? However, let's try this. I have here a piece of magnesium which burns very brightly. You might be able to see this burning magnesium through there. So I doubt you can see the flame with them on. Can you see the flame or not? Probably not. But you might see the magnesium once it starts to burn. You see that? Yeah? Burns incredibly bright. And you were able to see that through those glasses? Yeah. So, the little demo. It's pretty crazy that magnesium can burn that brightly. So what do we have left? We have lunar eclipses, huh? So what do you think? Do you want to keep going and finish this eclipse thing, or do you want to have some time to work on older assignments? Other votes? You say finish it? What do you say? You said finish it, and you said? Okay, I guess we're going to finish. So we're going to go ahead and finish up the lunar eclipses. So notice the diagram again. Now the sun is hitting the earth. The sunlight hits the earth, and the moon, look how small the moon is compared to the size of Earth's shadow. So it's a little different because so much of the moon is darkened at the same time. So you get a total eclipse during that part of the view, and you get a partial eclipse on either side of it. Once again, a lunar eclipse starts and ends with partial, with total in the middle. But anyone on the Earth side could see that total eclipse of the moon, couldn't they? In fact, we have one coming up in a month, and I'll tell you more about it in a minute. So the moon is circling around the Earth, right? And it moves right into Earth's shadow and then out again as it's moving. Okay, so there's your description. So a lunar eclipse occurs when the moon passes through the Earth's shadow. It takes several hours and only occurs during a full moon. So what moon phase is it? Full moon, right? Only occurs during a full moon. It can be seen from the entire night side of the Earth, so they're easier to see than solar eclipses, and they're completely safe to look at, even with a telescope or binoculars. So what I'd like you to do is imagine that the moon is just one of these things here. And meanwhile, the Earth's shadow is going off in space. Do we always have a shadow, or is it only during an eclipse? Think about it. Does the Earth always have a shadow? Is the sun always shining? So is the Earth always blocking off the sun behind it? Right? There's always a shadow coming off of the Earth. So imagine where it says penumbra and umbra, that's our shadow going off into space. And the moon is moving along and moving into that shadow, and it disappears in the umbra and then comes out of it again at the end of the eclipse. That's what you would be watching if you were watching a lunar eclipse. Hopefully you will in just a month, although you have to get up pretty early in the morning for it. Oh, here's a video of what happens. Same idea. I kind of like that too. So this gray circle is the Earth's shadow, right? I don't know if you can tell back there, but it's actually a double shadow. And the moon gets darker, and it actually looks kind of red for a while. And we're going to talk about why it looks red. Here's our lunar eclipse. Here's oh, these are actual videos of it. So here's the beginning. Earth's shadow starts to cover it. Check this out. Does this show that the Earth is a sphere? Is it a spherical shadow? A curved shadow? Doesn't that argue that Earth is in fact spherical? It's not flat. So beginning of the eclipse is right here. Total eclipse, the moon starts to look reddish. And then the ending of the eclipse. And we're going to talk about that reddish in a minute. So the Earth's shadow starts to cross the moon. We get a partial eclipse. And we can see that Earth is curved from that shadow. Then the total eclipse is when the moon is completely covered, but it looks reddish because some light passes through Earth's atmosphere. And some people call this a blood moon. Other people call it a copper moon. It kind of has a coppery color. And then we get another partial eclipse at the end. The whole thing takes several hours. But it all happens in one night, only on the full moon. There's your moon phase, only on the full moon. So stages 1, 2, and 3, did you get those? Partial eclipse, total eclipse, partial eclipse. No diamond ring effect. Okay. Total eclipse, partial eclipse. Starts and ends with partial, and you have total in the middle. So here's what's going on. Here's the sun over there somewhere. The sunlight hits the Earth. Here's the Earth's shadow that the moon is moving through, right? But some of the sunlight goes through Earth's atmosphere and is bent. It's refracted. And that bent light gives the light a red color. And when that red colored light hits the darkened moon, we can then see the moon again as this kind of bloody coppery color. It's not direct sunlight that it's hitting it. It's being refracted by Earth's atmosphere, changing it to this reddish light. Just like we see the red light at sunset and sunrise from the bending of the light. So for the blood moon description, that's just something like um, during the total lunar eclipse, the moon looks reddish when it's during the total phase. For the cause of it, that's where you would say sunlight is refracted by Earth's atmosphere so that the red light hits the darkened moon. Rose? Thank you. And then for your diagram, something like this. So remember, to get different colors out of pure light, out of white light, we have to bend it. Like a rainbow is because the raindrops are bending the light. And the more you bend it, the more different colors you get. The amount of bending is what defines what color you would see. So in this case, it's bent at the correct angle so that the light becomes red. And then when that red light hits the moon, it makes the moon have this so-called bloody appearance. Okay, so let's see. Here's a whole chart showing future lunar eclipses from 2021 to 2028. Look how many there will be. Now, they're not all total lunar eclipses. Some of them are partial eclipses, right? And they are visible in these parts of the world. And they can tell you how long they last. But we have one coming up in just a month, 1 month away. So we're going to have a total eclipse of the moon on May 26th at 4 in the morning. It will actually begin at 1:45. The eclipse will begin at 1:45, and then it will, you know, progress through the partial phases until at 4:18 we should be able to see the blood moon. And the reason that it says that it ends at 5:45 because that's sunrise. So to see this eclipse, you'd have to stay up or at least get up in the middle of the night. Um, it doesn't change very fast. So what I would advise doing if you want to see this is set an alarm for like 2:30, get up, have a look, go back to bed, set your alarm for 3:30, get up, have another look at how it's changed, go back to bed, set your alarm for 4:15, and then watch it for 15 minutes or so, and then go back to bed. If it was in the early hours of the night, then I would say just watch the whole thing. But it doesn't change that fast. It's going to be pretty late at night. So have a look, then go back to sleep and look again a while later. I like this photo because we can see the shadow of the earth. You see that? Where this is all the shadow of the earth making this nice circle and the moon is moving through it. And then it gets that blood color in the middle of the eclipse. And there's the blood moon. So this year we're going to have actually 4 eclipses around the world. We have a total lunar eclipse here in May. In June, there's an annular ring-shaped donut eclipse in Canada. In November, a partial lunar eclipse. Looks like we'll be able to see that here too. And then there's a total solar eclipse, but you have to go to Antarctica to see that. Or you have to be in a ship or in a jet. So I think this is an amazing photo because you can see both the corona and the prominences. So it's more like what your eye would see during a total eclipse, where you can see both the pink eruptions and the white streaming light coming out. Similarly with this one, has great views of the coronal streamers. So this is what we're supposed to draw for that last diagram, is the view of what a eclipse looks like. So what I think you should do is make a circle, and then you should use a red pen, a red crayon, whatever, to draw these prominences. And then you can just use like a black pencil to draw the corona and the streamers coming off of it. So that's your final drawing at the bottom of the notes. Should be what we see when we look at an eclipse. And then include these different labels. All right, when you're done with that, hopefully the whole thing is done. You can save it and upload it to get some points for your participation today. So turn that in. Um, and then I want you to think about what planet you would like to do your project about. I'm hoping that everybody does a different planet so we don't have like 7 different presentations about the same planet, right? So maybe choose your top 3. Um, and then start thinking about what you would like to do. And in the meantime, we still are going to study the sun, comets, meteors, and asteroids. We'll have an assignment where everybody learns something about all the different planets, and then your project is you'll be the specialist on one planet. You migrated to
Mr. Fairley?
Yeah.
Um, does the 10% extra credit per day still count for the planetology project?
Well, it's not per day. It's just
Or
over.
per week overall, yeah.
Yeah. Uh, yes, it does. Uh-huh. And
Right,
the due date that is on there is not correct.
right.
Okay?
So what does it do?
You're going to have at least another week before you have to turn it in.
All right, thank you.
Yeah, so you've got a bunch of time on that. If you want to get it done early, yes, there is a 10% bonus.
Awesome. Thank you.
Eli, I don't like people eating in here.